So we have a notion of vector-valued functions, but ultimately the reason that we introduced this notion of vector-valued functions is so that we could do calculus with them. Right? We will see that the sorts of questions we want to ask about vector-valued functions will involve derivatives and integrals, but to define derivatives and integrals, you have to have some notion of a limit. Right? So how do limits work for vector-valued functions? Fortunately, they work exactly like you think they should work. So if you have a vector-valued function r of t, the limit of your vector-valued function at some t value a is just, well, it's the vector you get by taking the limit of the individual coordinate functions. Right? There's actually kind of a subtle reason why this is the only possible sensible definition of a limit for a vector-valued function, but really justifying that involves digging into the epsilon delta definition for a limit, and I'd rather not do that because you will look at that again later in your life if you take a 400 level analysis class where you do calculus over again, but with all the epsilons and deltas exposed. So I'll leave it for then. This seems intuitive enough that, I don't know, for now I don't think it really requires much justification. So as an example, let's find the limit as t goes to pi of this vector-valued function, cosine t, sine t over pi minus t minus pi, and t. Okay, so all we need to do is take the limit as t goes to pi of each individual coordinate function. So the limit of cosine t, we need the limit as t goes to pi of sine t over t minus pi, and we need the limit as t goes to pi of t. Now fortunately, two of these are straightforward, right? Because cosine t is continuous at t equals pi, so it's safe to just plug in this t value, right? So we can just plug in the t value. Cosine of pi is -1. Similarly, over here for our z coordinate function, t is continuous at t equals pi, and so we can just plug in pi and we get pi. Unfortunately, for our y coordinate function, this is not continuous at t equals pi because it's not even defined at t equals pi, right? If you plug in t equals pi, you get 0 over 0, and 0 over 0 doesn't give you any information about what this limit is. So we're going to have to work a little harder to figure out the limit in the middle. So limit as t goes to pi of sine of t over t minus pi, and right, so this gives us 0 over 0 if we just try plugging in t equals pi. But remember, if you get 0 over 0, this is a situation where we could use L'Hopital's rule. So let's use L'Hopital's rule to take this limit. Remember, what L'Hopital's rule says is that if you have a limit that gives you 0 over 0, replace the numerator with the derivative of the numerator, and the derivative of sine is cosine, and replace the denominator with the derivative of the denominator, which is 1. And then try taking the limit again. And this time we can compute the limit, because now when we plug in pi, we get cosine of pi, which is -1, over 1, and that's -1. Okay, so this limit that we were looking for is, right, the x-coordinate is -1, the y-coordinate is -1, that's the one we had to work for, and the z-coordinate is pi. Okay, so that's how limits work for vector-valued functions. Of course, as soon as we introduce the notion of a limit, the notion of continuity comes along with it. Okay, so a vector-valued functions is continuous at some t value a if the value of the vector-valued function at a is equal to the limit of the vector-valued function at a. So this is exactly like the definition of continuous for real-valued functions. It's just our function happens to be vector-valued instead of real-valued. So right, remember the way to think about the definition of continuity is that this is r of a, this is what happens at a, and the limit as t goes to a of r of t, this is what happens near a, and being continuous it says that what happens at A is equal to what happens near A, right? Okay. So for an example, let's look at this. Oh yes, because limits happen component by component. Of course, a vector valued function is going to be continuous exactly when its individual coordinate functions are continuous. So if you want to know about continuity for a vector valued function, just check the continuity of the individual coordinate functions. Okay, so for example, let's look at this coordinate function, 1 over e to the t plus 1, comma, sine of t over t. Is this continuous for all real numbers? T? Well, let's see. Where is this first coordinate function continuous? So we are dividing by something, so we have to be careful about, is this denominator ever equal to 0? Well, it's not, because e to the t, that's always greater than or equal to 0. So some number greater than or equal to 0 plus 1, this denominator is always going to be greater than 0. Right? It's never going to be equal to 0. It's never going to be negative either. So this x-coordinate function is continuous everywhere. That is for all values of t, so i.e. all t values. Okay, so let's check on sine of t over t. Well, because of the t in the denominator, sine of t over t is not defined at t equals 0, right? And if it's not defined at t equals 0, that means it's also not it's not continuous at t equals 0, right? Because if you look at the definition of continuity, right, continuity says what happens at A is equal to what happens near A. Well, if nothing happens at A, if your function is undefined at A, then there is no such thing as at A, right? So you can't be continuous if the function, you can't be continuous at a t value if the function isn't defined at that t value. So because our y coordinate function is not continuous at t equals 0, r of t is also not continuous at t equals 0. So r of t not continuous at t equals 0. Okay, well, what about other t values? Sine of t over t, well, the only reason that we had this problem is because we have this t in the denominator, right? So that denominator is 0 when t is equal to 0. If t is not equal to 0, well, the numerator is defined because you can take the sine of any number, and the denominator isn't 0 if t isn't 0, and so then we're dividing by something that isn't 0, and that's fine. So as long as t isn't 0, sine t over t is continuous, right? The quotient of continuous things is continuous as long as you aren't dividing by 0. Okay, so our vector valued function, its coordinate functions are continuous everywhere for the x-coordinate function, and continuous when t is not equal to 0 for the y-coordinate function. And so where do these things overlap? Well, when t isn't 0. So r of t is continuous for t values that are not equal to 0. Okay. One other question, how could we slightly modify the formula for this function so that it is continuous for all t values? That's what I meant to ask, for all t values. Well, we already have a vector valued function that is continuous for every t value except t equals 0. So let's change r of t only at t equals 0, right? Leave the rest of it the same, because t equals 0 is the only place where r of t is not continuous. Okay, so what should we, I guess the question is, what should r of 0 be, right? R of 0 is not currently defined, so we have to come up with a value for it. Well, if we want continuity, then r of 0 is going to have to be equal to the limit as t goes to 0 of r of t, right? So I guess that makes us ask, well, what is the limit as t goes to 0 of r of t? Well, it's the limit as t goes to 0 of our x-coordinate function, which is 1 over e to the t plus 1, comma, and then the limit as t goes to 0 of our y-coordinate function, which is sine t over t. Okay, so to make our function continuous at 0, we have to choose r of 0 to be whatever this limit is. So let's compute this limit. In the x-coordinate function, well, this coordinate function is continuous at 0, so we can just plug in 0. We get 1 over e to the first power, so 1 over... Oh, actually I made a mistake writing down this function. This is 1 over e to the t plus 1. That plus 1 is not in the exponent. So the limit, we plug in t equals 0, we get 1 over e to the 0th plus 1, so that's 1 over 2. And then for the y-coordinate function, well, we can't just plug in 0 because we get 0 over 0, so we're going to have to take the limit of this. But since we got 0 over 0, we can use L'Hopital's rule and instead take the limit as t goes to 0 of the derivative of sine, which is cosine t, over the derivative of t, which is 1. So plug 0 into this, and we get 1. So to define what r of 0 has to be, it has to be 1/2 comma 0. So I guess we can, to write down a sort of full function, or a full formula for our vector valued function, the x-coordinate function we don't have to change at all because it was fine. All we need to do is we need to change the y-coordinate function. So as long as t isn't 0, we can use the formula we had before, which is sine of t over t. But if t is 0, well, to make it continuous, we have to choose the value 1, like this. So our y-coordinate function turns out to be a piecewise function like this. So now this r of t is continuous for all real valued t's.